Can Intel Optane memory compensate for less RAM? I currently have a laptop that is about 2 years old, and has 8 GB of RAM. I use my laptop for internet browsing, productivity applications, and programming, including data science within Spider or RStudio. I'm running Windows 10. I usually sit around 65% memory usage, or 5 GB roughly. I recently purchased, but haven't yet received, a laptop which has 4 GB of standard RAM, and 16 GB of Intel Optane memory. The laptop was marketed as having 20 GB of memory, but after reading more about Optane memory, it seems that it serves more as a low-latency cache than as RAM. For the purpose of running several memory-intensive programs simultaneously, for example browser with many tabs, data science IDEs, which average 5 GB of RAM usage, will decreasing RAM from 8 GB to 4 GB but adding 16 GB of Optane memory cause a performance slowdown? Here's a snapshot of my current memory profile if it's helpful. Update: if you're curious, I was able to cancel the order without issue. The answers helped me realize that the new purchase would have most likely been slower than my current laptop.
Intel Optane memory is a misnomer. It is just a cache memory card that can turn a simple hard disk into a hybrid disk, by adding a RAM cache that can work at the speed of an SSD disk. Optane memory isn't a random access computer memory, or RAM. Instead, it's meant to work as a cache memory bridge between RAM and storage, allowing for faster data transfer between the memory, storage, and processor. As such, it's magnitudes faster than a spinning hard drive and can work at the speed of a budget SSD. And like SSD, it doesn't erase itself when powered off. Conclusion: you did make a mistake by falling for a commercial hype. In addition, 4 GB of RAM is ridiculously low in our current state of hardware and software. I would advise canceling the order for this laptop, if you still can.
The other answers cover the gist of the situation, but I'd like to add some context. For a long time, RAM has been often called memory in laptops targeted at the layperson. This is usually helpful and hasn't caused issues, until recently. The same companies that started this practice are now lumping Optane cache and RAM under the same name memory with the intention of tricking you into thinking that the laptop has more RAM than it actually has. Optane technology is still relatively new and unknown, so this deception is very easy to fall for. Looking deeper into a product listing will usually reveal the truth. Optane cache doesn't, and wasn't meant to, replace RAM. They both help speed up a computer, but operate differently and in different situations. Having Optane won't alleviate the heavy slowdown of only having 4 GB of RAM when normal use requires at least 5 GB. You've fallen victim to intentionally deceptive marketing. I recommend purchasing a different laptop, with 8 GB or more of RAM, to satisfy your use case. Perhaps one from a more upfront manufacturer.
In this context, budget consumer gear, Optane is pretty clearly just referring to a small/fast and connected SSD using 3D point memory, instead of non-flash, giving it a very high write endurance. So it won't wear out if used as swap space. This is still going to suck for many workloads, because it still takes a page fault in many microseconds to access, versus 70 nanoseconds for a DRAM access, cache miss. It's not directly memory mapped on the PUS memory bus. Also, out-of-order execution, HW prefetch, other memory parallelism can keep 10 cache misses in flight per physical core, but a page fault is serializing. No useful work can be happening in this thread, while the OS is servicing a page fault, so there's no opportunity for UEXEC to hide any of that hard page fault latency. But even 70 ns is too long to fully hide anyway. Still, having multiple misses in flight to different lines goes a long way toward mitigating it for some workloads. Using a cripplingly small amount of RAM and depending on a fast SSD for swap space, page file is not the only use case for this kind of Optane. And probably not even a good use case. As this URL describes, its main use case is as a transparent cache for a magnetic hard drive. I think Intel provides Windows drivers to make this happen. You can buy SATA hard drives that have rotational magnetic storage with some flash built in as a buffer, cache for frequently accessed parts of the disk. Optane HW Plus drivers can do this for any disk. Optane NVMe apparently has very good random read performance at low queue depth. Wait for one read to finish before starting another, which unfortunately does happen when a program has to read one block before it can figure out what to do next, and software prefetching isn't helping. So it should be great at speeding up program start times, and boot up. Not particularly amazing for large contiguous writes of big files. Hopefully the driver software knows to bypass the Optane cache and go straight to the underlying magnetic disk for that. Intel's main Optane page links to this URL, which shows their 16 GB M.2 Optane has 900 MB/s sequential read, but only 145 MB/s sequential write. The 32 GB version is faster, at 1350 MB/s read, 290 MB/s write. But again, those aren't what Optane is best at. Its sequential and random read IOPS are both 240K IOPS, with 7 microseconds read latency. Intel has something called IMT, Intel Memory Drive Technology, which is a hypervisor that creates the illusion of a larger main memory address space for the operating system. Some pages will be mapped to the actual DRAM main memory while others are mapped to the SSD memory. When a page mapped to the SSD is accessed, a page fault occurs caught by IMT, which will cause the page to be brought from the SSD to main memory, potentially evicting a page from memory to the SSD. IMT will try to prefetch pages into DRAM to alleviate the inferior bandwidth and latency of the SSD. It will also try to keep the hottest pages in main memory so that they can be accessed with minimal penalty. The only penalty may come from the additional paging layers due to virtualization. The OS is mostly oblivious to this mapping and works normally. This kind of memory system is called software-defined memory, SDM. The nice paper titled Evaluation of Intel Memory Drive Technology Performance for Scientific Applications provides a performance evaluation of it and compares it against a system that has the same amount of DRAM main memory. I've not thoroughly read the paper, but it appears that it can migrate pages between NUMA nodes to get them closer to the node where they are mostly needed. That said, IMT is only supported on server-grade Intel processors. It's intended to create cost-effective, power-efficient servers with a potentially small impact on performance. This URL has some benchmarks with an Optane DCP4800X SSD. The high-end data center version, not consumer stuff. Much higher sustained write capability. I haven't looked into this, so I'm not sure if it's relevant at all for how Windows could take advantage of a consumer Optane SSD. The Optane brand name is, somewhat confusingly, also used for a much more interesting exotic thing. 3D point non-volatile DIMMs, aka Optane DC Persistent Memory. This URL. Apache Pass is the name of the first-generation Optane DCPM. Refer to this for information on future generations. Intel has their own mostly marketing page for it here, with some links to tech details. The DC stands for data-centric, apparently. This is non-volatile storage that plugs into a DDR4 DIMM slot, and appears as actual physical memory. Apparently it's only fully supported by next-generation Xeons, not the current Skylake X aka Skylake Scalable Processor series. There are other kinds of NVDIMM, for example battery-backed regular DRAM, optionally with flash to dump the data to for long-term power off, so they only need a supercapacitor instead of a chemical battery. This URL has some details. This URL has some more general info on NVDIMMs, and JEC standardization of them, and how OS+ applications can cooperate to let applications talk directly to a region of memory-mapped NV storage, ensuring commit ordering and so on. The main point is that they actually blur the line between RAM and storage, in a computer architecture sense, not in the strictly marketing sense of the deceptive laptop that you saw that claimed 4+16 GB. The OS can let a process map this non-volatile physical memory into their own virtual address space so they can access storage directly with user space loads and stores to memory addresses, without any system calls, letting the CPU hardware continue out-of-order execution while there are outstanding reads/writes. There are software libraries to let developers take advantage of this, including the ability to flush and make sure that data is actually written to persistent storage. This mapping can even be write-back cacheable, so usage of the data benefits fully from L3/L2/L1D cache until it's time to write it back, if modified. For read-mostly data, this kind of Optane really could justifiably be called 4+16 GB of RAM. Of course, the current data center use case for Optane DIMMs would use much larger DIMMs, like 512 GB. It's not like an mapped file on a normal disk where you just map the OS's page cache for the file, and the OS takes care of doing I/O in the background to sync dirty RAM pages with the storage device. Making sure some data has actually reached NV storage before others, to allow crash recovery like a file system or database journal, is essential. With system calls, this is where you'd use POSIX sync or FATASync. But since the application has the storage truly memory mapped, this is where library function calls come in. In x86 ASM, we're accessing storage with normal loads/stores, but we care about when data is actually written back to the NVDIMM, where it's safe from power loss, not when it's visible to other cores or to cache coherent DMA. As soon as it commits from the store buffer to L1D cache, so x86's normal memory ordering rules don't completely take care of everything. We need special instructions to flush selected cache lines from the CPU's cache, for use by the NV storage libraries. The cflush ASM instruction has existed for a while, but NV storage is a major reason why Intel added cflush Optane Skylake, although it has other use cases, too, and is adding CLWB in Ice Lake, write back without eviction. Dan Liu wrote an interesting article a while ago about the benefits of taking the OS out of the way for access to storage, detailing Intel's plans at that point for cflush, CLWB, and their memory ordering semantics. It was written while Intel was still planning to require an instruction called pcommit, persistent commit, as part of this process, but Intel later decided to remove that instruction, deprecating the pcommit instruction has some interesting info about why, and how things work under the hood. This got way off topic into x86 NV storage low-level details. I should find somewhere else to post most of this section, but I think it. There are also Optane DC SSDs, as a PCX4 card or 2.5 inches. The 750 GB version does up to 2500 MB/s sequential read, 2200 MB/s sequential write, and 550,000 IOPS random read or write. Read latency is slightly worse than the M.2 num, at 10 microseconds. This is what you want if you for a database server or something, if you can't use NVDIM, but it wouldn't make your 4GB laptop much faster, for most typical use cases, than the 16GB Optane they sell it with. Swap space thrashing often produces a lot of dependent reads as a page has to be paged in and accessed before the code that page faulted can continue on to whatever it was going to do next. If memory is really tight, the OS doesn't have spare pages to aggressively prefetch into, so you'd expect low queue depths, which the consumer Optane is optimized for. Low latency. The Intel Optane SSD offers a nice performance power-cost trade-off. SSDs basically don't consume power when not accessed. In contrast, the static power consumption, mostly due to refresh, in DRAM chips is significant. So the amount of DRAM in a system should ideally match the working set of the typical workload. The system you've purchased was designed for a typical workload that requires about 4 GB of main memory or less. In this case, if the system had 8 GB of main memory instead, it will unnecessarily consume more power, which would reduce the battery life. However, the Optane SSD allows you to occasionally run workloads that require slightly more main memory with minimal performance degradation, compared to NAND-based SSDs or HDDs. DRAM memory currently costs about $4.50 per 1 GB, while Intel Optane SSD costs about $2 per 1 GB. So a 16 GB Optane SSD is more expensive than a 4 GB DRAM module, but cheaper than an 8 GB DRAM module. So if you take out the Optane SSD and add 4 GB more memory, you'll get a cheaper system, which is also faster on average for typical workloads with larger than 4 GB working sets. But hard page fault handling, page prefetching, and page swapping would be slower from the HDD. That's why the 8 GB system will probably be slower than the 4 GB DRAM plus 16 GB Optane SSD system if the typical workload requires less than, or about, 4 GB of memory. Your laptop is great if you're just going to use it for internet browsing or text editing. The Optane SSD helps with boot time, provides quick access to the most frequently accessed files, and can be used as an additional secondary storage. So although you're paying more 16 GB Optane SSD than 4 GB of DRAM, you're getting certain, unique benefits for that. But some of the other applications you mentioned, such as RStudio, require a minimum of 4 GB memory. If you'll typically use a browser and RStudio at the same time, and maybe other apps, then you should get a system with at least 8 GB of memory. Optane SSD is still good to have though.
Only 4 GB? I hate to break it to you, but to the full extent of my knowledge, which isn't much, Intel Optane is not like memory aka RAM. It's like an SSD that takes the applications you use most and puts them on a faster drive so they load faster. So an Intel Optane drive might eliminate the need for an SSD. Please feel free to correct me on this. Your manufacturer probably put an Optane drive in your laptop and marketed it as RAM because 20 GB of Intel Optane is cheaper than 20 GB of RAM, but maybe you can manually change the RAM to 8 GB for about $80. 24 GB of laptop RAM $182. 24 GB of laptop RAM. $4 GB of laptop RAM and 16 GB of Intel Optane memory $87. Laptop RAM. Intel Optane memory.
If you want to support the channel, please consider subscribing.